Okie dokie. Well, it is my pleasure to introduce today our speaker for Cool Things, Dr. Markus Eberl, an associate professor in the Department of Anthropology. And we're especially excited because he has recently been awarded the Faculty Mentorship Award from the Department of Anthropology for his excellent mentorship of graduate and undergraduate students. So we are so proud to have him with us here today. A little bit more about Dr. Eberl. He's an archaeologist and in the Department of Anthropology at Vanderbilt. His research focuses on the subjective experience of life in ancient societies with a particular emphasis on Mayan communities. Specifically, he works to reconstruct past societies by examining communities as key social features, analyzing symbols and communication, and documenting social change. So today he's going to be talking to us a little bit more about his work, analyzing soil samples to understand the civilization structure of an ancient Mayan community. Thank you for joining us today, Dr. Eberl.
Yes, so thank you, Dr. Bell and Dr. Spencer-Smith for inviting me today. And let me try to work this. So my plan is, let me just try this screen. And hopefully this should work. So I have, wait a minute. Okay, can everybody see this? So basically, I work as an archaeologist in Guatemala.
Oh, I don't think that we can see it yet, though.
Oh, wait a minute. Then
you see your profile picture.
Oh, sorry. Then let me just try this again. Start screen broadcast. Okay.
Oh, there we go. Perfect.
Okay, perfect.
Oh,
well, thank you so much. So yes, so thank you, Dr. Bell and Dr. Spencer-Smith for inviting me today. And what I hope to talk about is, well, as you see it in the title, how I came to love big data. Specifically, I mean, as you see it here from the photo, I really started working as an archaeologist who was stumbling around the rainforest of Guatemala. And my interest was always to understand the life of people who were living about 1,200, 1,300 years ago. And during my excavations, I excavated prismatic plates, chert pieces, sort of regular stone tools that you see in the upper right corner. And my interest was always like, how did the Maya produce these stone tools? Where did they produce them? And specifically, the problem for me is that stone knappers, be it the ancient ones or the modern ones, they clean away all the debris in their work areas. Because normally in ancient and modern times, stone knappers work literally next to the residence. At the lower right, you see a modern Lacandone Maya house with the stone working area outlined in red. So literally there are kids stumbling around, there are other people walking by, and stone knappers don't want to have anybody walking into sharp stone debris. So normally they clean all of that away, and that makes it difficult for me as an archaeologist to figure out where did the ancient people actually knap stone. And I talk about it today as one of the examples to exemplify how I, or archaeologists in general, can use microscopic evidence to reconstruct what humans were doing hundreds or even thousands of years ago. Now, in the case of microdebitage, the idea is relatively simple. What you see here is a drawing of a conchoidal flake. So this is one of the flakes that a stone knapper produces while knapping stone. It has specific features that are identified here. It has ripple marks. You see the platform where the hammer or the tool strikes the stone. And then most significantly, there is a bulb of force that really shows, oh, this was done, this flake came off during the production of a stone tool. And so I thought, this is going back 20 years as a graduate student, oh, that's fascinating. I should try to figure out whether I can identify this debitage in ancient soil samples. And what you see here is a photo of a landmark publication that was published in 1982 that seemed to suggest, well, this is actually pretty straightforward. What you see here are photographs of microdebitage as it was published. I highlight that here in green and yellow because in both cases, microdebitage is mixed in with lots of other stuff. In this specific case, quartz sand. And You will probably enjoy this photo of me. This is like literally in 2002 when I collected my first soil samples, sieving through them under a microscope. And you see me here working on the left side. On the upper right side is a photograph of one of the soil samples. And on the lower right side was one initial step that I did, because I wasn't quite sure how would the microdebitage look like? What should I be looking for? So I collected dirt in the field as part of my excavations, and then I made experiments to produce some microdebitage on my own. What I quickly realized is that this type of manual analysis is not really as straightforward as the publications suggested. First, I realized that actually the amount of particles that I have to sift through is literally overwhelming. I mean, I now know that there can be easily 500,000 particles in one soil sample. And what you see here on the right side, this box contains about 200, 300 samples. The second part that I realized is that simply looking through a microscope at the soil samples is super tedious. I mean, you look at hundreds of thousands of particles and you try to find a few that are microdebitage. So this meant that all the publications that I have encountered so far, they are limited to about 100 samples. Simply people didn't have time enough to really investigate that issue in depth. And the second part, what really irked me, is I didn't really find very consistent description of what microdebitage actually looks like. I mean, how diverse is it? Are there objective parameters that I should look for? So what happened, I mean, so as you see it here, I collected the first samples in 2002, and then I basically gave up. I was like, okay, this doesn't really work for me as I was hoping for. Then in the last years, I'm started to tackle the inherent issues. So first of all, I wanted to get objective data on how microdebitage actually looks like. So I'm working together with a stone napper, whom you see here, Mike McBride, who came actually to Vanderbilt to reproduce modern stone tools with traditional materials and ancient techniques. And as part of these experiments, we would collect all the stone debris in Ziploc bags, and we would mark them as you see it here, Mike and me collecting the debris on the left, and then the debris itself on the right side with a finished stone tool, the biface at the bottom. So we have here now extensive data on how microdebitage should look like. The problem was, well, how do we actually analyze it? As you saw it, I mean, I now know that soil samples contain about 500,000 particles. And with several hundred soil samples, I'm easily running into millions, if not billions of particles to sift through. And clearly doing it manually probably wouldn't really work. So my first thought was, well, I should try to find a 3D scanner. And lo and behold, there is actually something that you see here on the screen that is widely available. Unfortunately, it costs about $30,000, and it actually provides the proper resolution to identify individual particles. The problem is you have to put in each particle by hand, and actually, as the representative told me, you actually have to turn it around to get a full 360-degree scan of each particle. And you can imagine with 500,000 particles in each sample, this is not gonna work. So then it happened about a year ago that this was like a late night Googling accident that I came across a new type of particle analyzer, specifically a dynamic image particle analyzer that is the Parton 3D. And that is now just behind me in the lab. And I'll actually show you in a minute how it works. This particle analyzer is really amazing because it measures about 40 variables for each soil particle. So meaning from each sample, I get about 500,000 entries and 40 variables, 40 measurements for each particle. And more importantly, each sample can be processed in about 5 minutes. So which means it opens the path for me to analyze thousands of particles. And I'm now working with Dr. Bell and Dr. Spencer-Smith to apply machine learning to actually score each particle to differentiate between microdebitage and actual or just regular soil. And we use the experimental data to define how microdebitage should look like. So the goals of the Ancient Artifacts project is, in generally speaking, I want to identify the lithic microdebitage. So this will help me to know where ancient Maya napped stone in specific places. So I hope to apply this method to hundreds of samples or even thousands of samples. And ancient stone napping was a critical component of the ancient economy. We call it ancient artifacts because eventually we hope to extend this approach, machine learning and particle analysis to other materials. And most importantly, what I learned from this entire process, it's really emblematic for data science potential for the humanities and social sciences, that suddenly I'm now seeing new approaches to previously impenetrable problems. And so we can really look at issues that previously couldn't be solved in traditional manual analysis. So this is here a little bit of my the background, and I will now try to actually run a sample for you so that you actually get to see what the particle analyzer does. So let me open here is, of course, it doesn't really work as, wait a minute. So, okay, so what you'll see. So what I'll show you here is the entire setup. So you have the screen in front of me, you have the particle analyzer in the back. You will now see also an ominous hum. This is the vibrator that moves particle, do that, that moves the particles into the chute where they are measured. And I'm just gonna do this. Okay, let's just do this, start analysis. So what this first is doing, or what it should be doing, and it's of course not quite there. What is happening? Ah, okay, open. Okay, nope, I'm sorry. This is what I feared would happen. The particle analyzer is acting up. Well, let me see, or I think I have to do a few things. Okay, let me do this. Okay, let me try this again. So, new analysis, and open this. Okay, PM, let's do this, and I'll start the analysis. So what it should be doing right now is it's connecting to the particle analyzer in the back. And what I'm waiting for is that it should auto mask, and it doesn't do it for reasons that I'm not quite comprehending. Okay, okay, I think this is not quite working as hoping for. So I don't know, Dr. Spencer-Smith, should I try to troubleshoot the particle analyzer, or Dr. Bell?
It's definitely okay. I know that sometimes technology gets super camera shy. It sees a real demonstration and it's terrified.
Yes. Okay, this is, let me try. This is something interesting. I just tried it before this presentation and it worked. And of course, now, let me just try this again. Okay.
Sometimes over a couple of times.
Pardon me?
Sometimes I have to close out and start it a couple of times before it will mask.
So yes, so I'm actually just seeing that. Let me just auto masking. Yes. So let me just do this. It's doing something now.
We might want to try again a little bit later too. My internet went completely down, so I don't know if the recording continued after the I don't know what's happening. They're doing something with our cable again. So we might actually want to get another recording perhaps. So it would be all right if we ran it again, if we watched it run again another time.
Actually, I mean, if it's okay, I'm actually, this is right now working. So let me just show you what's happening. So I poured in some soil here into the funnel. You see it, the soil falling here into this chute, and you see the backlight. Yes. And what I'm now showing you here is the particle analyzer itself. So this is the camera view rotated by 90 degrees. So it's falling from the left to the right. And what you can see, I mean, probably it's hard to realize right now, the camera software identifies each particle. And I'm just going to stop the analysis so that you can see the outcome. So what it does is the camera software, okay, I'm saving that. It measures each particle and tracks each particle as it tumbles down the chute. And what I'm now doing is what you see here on the screen is it takes multiple photos of each particle. So in this case, each line represents several images of the same particle, and it provides then individual data on each particle. And this is, I'm just going to close in so you can see each measurement for the particles and the images that would correspond to each of these particles that the particle analyzer delivers. So this is the outcome for what I'm hoping to use in archaeology, but it's also be hopefully interesting for quite a few other disciplines here on campus. So yes, so I think it worked in the end. So thank you all for working with me through the hiccups of the machine. But yes, so this is like what I hope to use in the future, and with the help of the Data Science Institute to also make sense of all the data with machine learning. So thank you all.
Yes,
that was incredibly cool.
I know, that was the coolest. And I think we see so many messages in the chat and are just like, oh my gosh, that's so cool. This was such a great approach that you came up with. And I think this is so cool. What a great way to look at so many particles at one time. This is just absolutely fantastic. Thank you so much for showing this to us today.
Thank you.
So cool.
Absolutely, yes.
I think when we get back on campus, we're going to have to find some particles to analyze. We just want to see. Does anyone have any questions for Dr. Eberl? All right, great. Well, please feel free to follow up with us or Dr. Eberl at your leisure. This will be posted on our YouTube channel. And I think that's the end for us today. Thanks again for coming, Marcus. We really loved your presentation. So cool. And I'm sure we'll get lots of views on this one.
Okay, thank you all.
Thanks, Marcus.
All right, well, everyone have a great rest of your Friday, and thanks again for coming.
Okay, bye-bye.